So just a quick warm-up, because I believe this talk and the next talk will be core protocol development things. So it might be boring to some of you, or it might be very interesting if you work on corpor like myself. I'm just curious, like if anyone runs a node on Ethereum, whether it's testnet or mainnet, anyone? Okay, I see one there. Only one? Okay. I expected more, but it's fine. I know it's hard to run a node, but anyways, I personally run a node on Ethereum mainnet and testnet, and definitely also Starknet. And I remember my first experience running a node 2 years ago was when I had to gather a bunch of hardware, making sure that my network setup is right. And when I finally got everything right, I pressed the start button. So I expected it to sync for a day. But to my surprise, it actually took 30 days and actually even more. So then I wondered, like, is there a better way of syncing? Like, no, definitely I was very surprised that, I was very happy that my node is synced after 30 days, but to me at that time, it just feels very slow. So I did some digging to my setup, and I realized I was running on a configuration called full sync, not snap sync. So after that, I think after a few weeks, I bought another pair of machine. I had the same exact setup, and then I ran it on SnapSync. And I managed to sync the node in just under a week. So that's how powerful SnapSync is as compared to the regular full syncing experience. I'll explain what those things means later on. But at the same time, I do not want to trick you to think that SnapSync is the end game solution. SnapSync is the best way of syncing a node on any blockchain or anything else, because in fact it's not. And there are much better syncing algorithms out there. And at the end of today's talk, I'm also going to share with you how the future of syncing looks like. But without further ado, let's dive a little bit deeper into how SnapSync works on Ethereum. So first, let's think from first principles, like why do you even have to sync a node, like when you run a node? So typically on a blockchain system, you would have two roles, two actors in general, or two important ones. You have the block producer, and then you also have the block validator. So basically, as the name implies, block producer proposes a block or produces a block, and then the block validator basically would validate a block. So just assuming that the system is this diagram, you only have these two actors without anything else. It's basically a trust me both system, because you're just the block validator would be just trusting whatever block that it receives. But of course, it's a blockchain, so we don't want to have this kind of trust me both system. This is where we get the I don't trust you, that kind of thing. That's where you have to verify if the block is correct or not. So in order to verify if a block is correct, you basically have to introduce something called a state, right? So both the block producer and the block validator have to have the right state and also the latest one. So in order, for example, for block producer, they need the latest state in order to produce the right results. And for block validator, they need the latest state in order to validate that this is correct. So now, again, from first principles, what exactly is a state? On Ethereum, the fundamental data objects are basically these two things, accounts and slot values. So an account, two types, EOAs and contract account. So EOAs are externally owned account, basically a regular account with just the balance and also nonce. And then you have contract, which is your contract. And so for each contract, it will also have its own slot values. So two fundamental data objects, account and slot value. And how are these objects being represented? Is by using a cryptographic structure called TRI, or Merkle-Patricia TRI, or to be even more specific, hexary Merkle-Patricia TRI. This diagram is a binary one to make it simple, but in actual cases, it's actually a hexary Merkle-Patricia TRI or a hexary MPT. So you start off by having the state TRI, or other people may call it the account TRI. So in the leaves of the state TRI, you would get all of the accounts. So account contain balance, nonce, root hash, and code hash. And then for each of the contract account, you would get the storage TRI, right? And the leaves of this storage TRI will basically contain all of the slot values, 32 bytes, raw bytes, right? So This is how a state is being represented. So when people mention, yeah, we need the state, we need the state, we need the state to sync, it's basically, what they mean is basically we need the latest state try to sync, right? So this is the kind of the general picture of what we need. Now, let's talk about full sync, or let's talk about one of the most naive approach when it comes to syncing a node, which is, we call it full sync. So how full sync works is, again, very naive. You start from zero, you start from scratch, you start from the genesis. You take the genesis block, you execute it, you get a state, and then you take the next block, which is block number 1, you execute it, you get the next state, and then you keep doing it as the chain progresses and until you have reached the latest state or latest block, right? So as I say, this is naive, and the problem with this is it's way too slow. If you attempt to do this on, for example, someone at a low-end machine or a Raspberry Pi, that kind of setup, doing a full sync will probably take you, from my experience nowadays, I think probably about 2 months, 2 to 3 months. So it's way too slow. But if you have to run an archive node, then you have no choice. Using Go Ethereum or Nethermind, if you are using Aragon or Rev, or yeah, these two clients, then they have their own syncing mechanism, which is much faster, but okay, I'm not gonna talk more about them because I don't know much about how they sync, but anyways, yeah, it's too slow. So going back to the goal of syncing, right? The ultimate goal of syncing is just we want the state try. And to be more specific, we want the latest state try. So how can we do that without executing block by block? And the answer is step sync. So how does step sync work? So first step is that you will select a pivot block. So a pivot block is basically you want to sync up until a certain point in time. Time means in terms of measured in block height. So this is usually the last finalized block, not the latest block. Why is it not the latest block? Very simple. Because if you choose the latest block, if you choose the latest block, this latest block that you have chosen could be reorged. So when it reorgs, that means if you have downloaded the state, you have to revert the state. So, and you revert the state and then you choose the second, you choose another latest block. And there's a chance that it might get reorged again, then you have to do the reverting process again. So this back and forth reverting kind of thing isn't ideal when it comes to engineering. It's not efficient, it's not effective. That's why you usually would choose the last finalized block because it's less likely to be reorged. But if in the worst case it is reorged, then the process, the step sync process will become very expensive in terms of the reverting process. Yeah. So anyways, choose a pivot block. Next, you would have to download the leaf ranges. So what do you mean by leaf ranges? A leaf here means, again, the fundamental data object, account or slot. So leaf ranges means it's either account range or a slot range. So a range is basically a range of accounts from one address to another address. So for example, the requester will request for the accounts for example, address 1 to address 3. Right? So that is a range of 1 to 3. So the requestee will send back the actual account objects back to the requester from account 1, address 1 to address 3. So that is a range. So assuming that the current Ethereum state try contains account from address 1 to address 10,000, if the requester has the account from 1 to 10,000, he or she can reconstruct the entire state try, right? Because that's how the objects are being represented. But there's one caveat here. What if the requestee is malicious? Or what if it sends back a false value, right? So there must be some way to prove that this range is correct, and that's where we need a proving mechanism. And here, the proof that we use is called range proof. So so the range proof will prove that this range is correct. To dive deeper into how does a range proof look like, let's give an example. So assuming that on the left side, you have the try, and then the account range that is being requested is from address 1 to address 4. So first step on generating the range proof is you're going to prove the left side, meaning to prove the first item or the first account in the range. So here you will generate a Merkle proof for the left side, and then you're going to generate a Merkle proof for the right side. So here in this example is account 4, which is the last item in the range. And then a range proof is basically merging these Merkle proofs together. So this is how a range proof will look like. So it's kind of like a partial view of the trie. So this is a range proof. In terms of the verification part, now you have two things. You have the range, you have the range proof. So in order to validate if this range is correct, you simply insert these values into the range proof, right? So again, now this becomes a slightly even more complete view of the entire state trie. So to validate if this is correct, you basically check the root hash. So if it's a state trie, you check if the root hash of this partial trie that you have just reconstructed matches the one in the block, or if it's a contract trie, then you will check if it matches the one in the account, right? So what happens if one of the values is false? So you basically get a mismatched root hash. So what will happen is you will reject this range, you will reject this response, and you probably would ban this peer because it sends you a false range. So that is a very simplified version of range proof. So after verification, if it's correct, the requester will simply persist the range into the database, and this process would repeat until all of the ranges has been downloaded. So yeah, that's kind of it for SnapSync. So it's actually much simpler than you might have thought, or is it? Not really, because there are a few more issues that we have to address. The first issue is pivot block constantly changes. So the pivot block, so last finalized block, it means that latest block minus 64, something like that, usually. So it's practically or almost impossible that you have downloaded all of the available state, meaning accounts or slots, within this period, or in this pivot block. It's practically impossible. So the pivot block would change, would definitely change, and when it changed, that means that the state you have downloaded before, they could be outdated, and there could be some missing gaps in your current available downloaded state. So that's one of the issues that we have to address. The second issue that we have to address is that we want the latest state, right? So because again, we are only requesting up until pivot block because of reorg issues, but this is still our final goal. So we have to introduce an additional phase called healing. So the healing process is that you have already downloaded all of the range, you have reconstructed a trie up until a certain point. Some of them are outdated, and then you compare it with the latest state trie, right? So you will see some, you would get some missing gaps or outdated values. So the solution to this is actually very simple. You simply request for the missing trinodes, right? So the requesters would request for the missing trinodes, and the requestee will send back the trinodes. And then you would replace the outdated ones or fill up the missing ones. So one very important thing when it comes to SnapSync during this phase is that you have to have a good network setup and also a good hardware setup such that you are able to heal much faster than the chain progresses. Because if you can't heal that fast, you will forever be in the healing phase, forever, stuck in the loop. And that's why when you go into like Go Ethereum Discord or go into Nethermind Discord, even check their hardware specification, they always emphasize a few things. One is that you need to have a certain amount of network bandwidth. The second thing is that you must use SSD. I don't think anyone can sync a node in using an HDD anymore. Maybe you can be 2 years before or even 3 years before, but nowadays it's practically impossible. So yeah, to recap, SnapSync, 5 steps. Select a pivot block, download all of the ranges plus the range proof up until that pivot block, verify the range, persist the range in the database, and then once everything is done, perform state healing, make sure it's fast enough such that you can reconstruct the state to catch up with the latest chain head. And from there, once you have caught up with the latest chain head, you can then do the regular syncing by executing block by block. So yeah, this is SnapSync. Next, step sync on Starknet. So, or any other layer 2 that uses a similar trie structure. So, a quick introduction of what Starknet is. It is a validity rollup, or some people may call it ZK rollup. And it uses Stark proofs, as the name implies. So, how would it work on Starknet, or how would it work in L2s? First, let's understand the differences between Ethereum state and also Starknet state. So, this is how actual state trie on Ethereum will look like. It's a hex array MPT, as I mentioned. And on Starknet, it actually uses a binary MPT. So, but there are two things here. I mean, two tries. One try is called contract try. So a contract try is the exact same thing as the state try on Ethereum. There's a second try called class try, which I won't dive deeper into it. But just remember that there are two tries. So how the step sync process will work is generally works the same. Yeah, I don't have an interesting answer for you because it's try structure. Step sync is to download try. It's a protocol to download try. So since we are still using a MPT structure, then it should generally work the same. A few things that are different are hash functions, state structure, and try structure. And one more additional fun thing that L2s can usually do is to leverage on the state diffs posted on L1s. I mean L1. So for example, since we post the state diffs via call data or blobs, so what L2 nodes can do is to extract these state diffs, decode them, and get the actual state diffs. And those would basically be a partial range. Right, you can use that as a range and persist in the database as well. So that's one of the things that can be done. But other things in terms of the general protocol flow, it should work the same. Now, the fun part, or the final part, which is the future of syncing. How would syncing look like for those who are running nodes? Will we have a better syncing algorithm? And my answer to this question is that ultimately, we will go into stateless sync. Okay, let the name sink into you a little bit. It's called stateless sync. And throughout the past 10 minutes, I have been talking about syncing to get the latest state. But now I'm talking about getting stateless sync to work in the future. This is the end goal. So how do we make sense of this? So in the future, very near future, maybe 2 years or 3 years, or even this year, we might have some demo. How stateless clients will work is that anyone can basically take a block without any prerequisites. You can execute the block and progresses with the chain. Why is that so? It's because in the future on Ethereum, if we actually go with the roadmap, the blocks will contain proofs, or what we call as witnesses, to prove that the state changes given in this block is valid. So that means, again, a block is a single execution unit, so we don't need the state anymore. Hence, this is why it's called stateless. Why it's good for us is because if you want to do block validation, you can simply run a node without any state. But if you want to produce a block, you still have to have predefined state. So this complements very well with proposals like EPBS, Proposal Builder Separation, where if you are just only interested in validating the chain with staking, you can just run a block validator, and your node will have a much, much lower hardware setup because you don't need the state, right? So that will also mean that it may be possible that we can run an Ethereum node just on our phone, because the hardware requirement is just so much lower. So this is a roadmap that I'm very excited for on Ethereum. If you want to know more about stateless clients or stateless roadmap, go check out stateless.fyi. This is an official documentation given by the Ethereum Foundation, specifically the stateless consensus team. So yeah, that's all. And I'm an engineer working in Nethermind. I particularly work on Starknet client called Juno. So if you want to talk to me about clients, protocol development, or just blockchain in general, do let me know. And thank you all for listening. Thank you.
All right, we have quite some time for questions. Any questions? Yes, sir.
Hi, thank you. Great talk. So, as a user, is there any difference when making an RPC call?
RPC call?
RPC call to a SnapSync server versus the full node server?
No, all the RPCs should work the same. Yeah, there shouldn't be any differences. But the difference of the RPCs would differ depending on the type of the node. So there's few types: light node, full node, archive node, or some maybe stateless node as well. So if we focus on full node and archive node. So for full node, so for archive node, it can answer all of the RPC calls. But for full node, it might not be able to answer some of the questions. For example, what is my account balance at block 100? So block 100 is like many years ago. So it definitely wouldn't be able to answer that. And maybe one of the calls could be get proof. So if get proof, so for full node on Geth and maybe also on Nethermind, it can only give you the proof up until 128 blocks before. So anything beyond that, you cannot get a proof for it. So yeah.
Okay, got it. So there's no performance difference?
Performance difference, no.
Okay. Another question. I'm curious about what is the hardware requirement for running a SnapSync node?
Hardware requirement for running a SnapSync node, oh, wow, I can't think of it. I mean, I can't recall it right now, but because they recently came out with not really, is it EIP? Like an official documentation to upgrade the hardware requirement. I believe it's 32 gig RAM, 4 terabytes SSD, 50 megabytes per second network, and yeah, and I think also some CPU recommendations or yeah, so somewhere along that line. There's some documentation online, but I'm still using the old one, which is 16 gigabytes of RAM and 2 terabytes of SSD. I might have to upgrade my hardware soon, but yeah.
Okay, got it. So it's much easier than running a full node?
If you value syncing time, yes. Okay. If you want to sync your node much faster, please use SnapSync and don't torture yourself using full sync.
Okay, thank you.
Any other questions? Cool. I have some questions actually. So kind of like, if you're gonna do like a TLDR, like SnapSync fast, right? Is there a downside to it?
The downside is that it's usually very CPU intensive. It's very resource intensive. So for Go Ethereum node, it's usually more stable. For Nethermind node, it's usually less stable because, I mean, based on my experience, 2 years ago, but nowadays I think it's much more stable. Because last time when I ran SnapSync on Nethermind on a slightly low end setup, it actually crashes because due to memory issues. But I think it will be it's more stable nowadays. But nonetheless, it's still going to be it's definitely going to take up all of your RAM, all of your CPU because it wants to be fast. There are a lot of things going on behind the scenes when you are snap syncing. So, yeah.
I see. Then perhaps on the question from another perspective, which is the users, right? So for the users who want to sync nodes, typically there are developers or like miners, right? For miners, you mentioned in the future, we might be just using the stateless ones. But who would be using just kind of like from your perspective, who would be using snap syncs later and other kind of syncs?
So I think the roadmap is that we will go with PBS, proposal builder separation. So that means there will be a clear separation between proposal and builder on a protocol level. So for someone like me who doesn't care about MEV, I don't want to extract MEV when I run a validated node, then I just want to validate if the chain is correct. Then I will run a stateless client to just validate the chain. And it's going to be much easier for me. The hardware setup is going to be much lighter. the commands or the instructions is going to be much better. That means the user experience is also going to be much better. So that will be one of the user profile. And then for block producers who are typically institutions who, quants who want to do some MVV stuff, or even RPC providers, then they will want to run the regular snap sync process rather than a stateless sync. So yeah, I think that would be quite interesting to see.
Awesome. Just want to make sure there's no other questions. Any other? All right, one last from me. Actually, I have a lot of questions. It's great talk, and so I'm very interested. One question that I have essentially is also coming from the user side. So as a user, like so I'm sort of ignorant on the node side of things. I'm more on the Solidity and just like the smart contract side. So it would be good to have your input. My understanding is that wallets, at the end of the day, we hope to have like light node. But is that practical nowadays? And do you see, like ideally it should be able to run on my mobile phone, right? But is it practical nowadays? And then, like how is it looking in the
Now, definitely no, with the current syncing mechanism or whatever protocol rules that we have. But as I said, stateless would start to enable this road or this opportunity. But I do see, like my goal is also that such that I want to be able to validate on my phone. I think stateless clients will be able to enable that in terms of the hardware side, but in terms of the networking side, it would have some issue because mobile devices, for my knowledge, mobile devices are bad when it comes to P2P networks. So that might be another hurdle that we have to overcome. But at least on the hardware side, at least on the execution side, it's kind of fixed. But on the networking side, we might have to solve it later on. But it's definitely feasible once we have stateless clients, hopefully in 2 years, optimistically, yeah.
Which brings me to an interesting follow-up question. I promise that this is the last one. I keep saying the last, but it's too interesting. So you mentioned that like on this direction, basically the stateless one will be enabling the mobile one. But on the light client, my understanding is that it still needed some state for that, or no, completely don't?
Light side, I'm not sure if live client is even needed after we have stateless. Yeah, I can't think of why. Maybe there are some users who want that, but I'm not sure why, because a light client ultimately relies on a full node to do validation correctly. So if you already have a stateless client, then why would you run a light node? So yeah, maybe there are some things that I've never thought of deeply, but personally, I don't think people will run a light node anymore after that, but yeah.
Interesting. That's very great insight. Essentially, after the stateless is ready, then light client is basically replaced by that. Should be. Like per current understanding. And
current understanding, yes.
Per current understanding, which means that could be an interesting topic to dive into later and then talk about in the next ETHTaipei or regular meetups. So let's thanks Han for the wonderful presentation.